In the next problem, I'd like to compute some improper integral. So consider this function cosine of x over x, and let's show that the integral of this function from pi over 2 to infinity exists as an improper Riemann integral, and then I will show that that integral doesn't exist as a Lebesgue integral. Okay, so let's first plot the integrand function. So as you can see, it's an oscillating function, and the zeros of this function are located at the points pi over 2, 3 pi over 2, and so on. Okay, so okay, let's define this f of x cosine of x over x. So f of x is 0 if and only if x is pi over 2 plus pi k for some integer k. Okay, so the improper integral, as we know, is defined as the limit of proper Riemann integrals where the upper limit b approaches infinity. So consider this integral, and let's apply the integration by parts. Okay, so we apply the integration by parts, and we obtain the following expression. So the first part is just the difference, sine of b divided by b, minus sine of pi over 2 is 1, okay, divided by pi over 2, plus the integral from pi over 2 to b of the function sine over x divided by x squared dx. Okay, so let's show that the improper integral of function sine of x over x squared exists. Okay, so to show that, we just need to find the dominating function. So the absolute value of this integral doesn't exceed the integral of the absolute value sine over x divided by x squared dx. And since sine over x is a bounded function, so the absolute value of sine over x is bounded by 1. So we obtain that this integral is bounded above by the integral of 1 over x squared. And again, as we know, this integral exists, right? So it's equal to 2 over pi, so it's finite. So therefore, the improper integral of sine of x over x squared exists. Okay, hence the improper integral of the original function cosine of x dx also exists and is equal to the limit of this expression as b goes to infinity, sine over b over sine of b over b minus 2 pi plus the integral of sine of x over x dx. Okay, so this limit is just 0. Okay, and then the other integral exists, is finite, but of course it can be computed only approximately. Now I'm going to show that the same integral doesn't exist as the Lebesgue integral. So recall you that a function is Lebesgue integrable if and only if the Lebesgue integral of the absolute value of such function is finite. So we need to consider the integral, the improper Riemann integral of the function absolute value of cosine of x divided by x from pi over 2 to infinity. Okay, so let me just denote again the integrand by g. So g of x is absolute value of cosine divided by x, and let me plot this function. Okay, so here's the plot. So as you can see, the function is actually oscillating, so the plot reminds me a path of a jumping frog, and the zeros of the function are actually the same as the zeros of the function f. So g is 0 if and only if x is equal to pi over 2 plus pi n for some integer n. Okay. Again, let me consider the proper Riemann integral with some upper limit b, and as upper limit b I will consider one of these zeros, so b equals pi over 2 plus pi n, okay, where n is now a natural number. So now this integral can be expressed as a sum of integrals over the joint subintervals. Okay, so now k changes from 1 to n, and we integrate over the following interval: pi over 2 plus pi times k minus 1 to pi over 2 plus pi k g of x dx. Alright, so let's analyze each of these integrals. Okay. So clearly the integrand can be approximated below by a ratio of the cosine function and a constant. So we just replace x by the maximum value of x on the integration subinterval, right? So in this case we can approximate the integral below as follows. So it will be greater than or equal to, okay, so again the same region, but now we have absolute value of cosine of x divided by pi over 2 plus pi k dx. Okay, so now if you want to compute this integral of cosine of absolute value of cosine of x, and because cosine of x is a periodic function, it's enough just to consider the integral from pi over 2 to 3 pi over 2. And clearly, okay, so in this case cosine function is negative on this interval, the integral will be minus sine of x pi over 2 3 pi over 2 and is equal to 2. Alright, so let's come back to our summation. So now each of the integrals here can be approximated below by just by a constant. Okay, so we have greater than or equal to the same summation, k changes from 1 to n, and now what we have that constant 1 divided by pi over 2 plus pi k times the integral of the absolute value of cosine of x, which is 2. Okay, and now I can rewrite it as follows. So it will be 2 over pi times, again, summation, k changes from 1 to n, and now I have 1 divided by k plus 1/2. So I can again change 1/2 to 1, so in this case each fraction will only decrease. So I have 2 over pi, then again same summation, and now I have 1 divided by k plus 1. So the point is, remember, if you consider this series, k goes from 1 to infinity, 1 over k, then this series actually diverges, so it's infinite. So therefore the left hand side of this inequality goes to infinity and then goes to infinity. So what happens? That what we did, actually we found a lower bound of this integral, and we show that this lower bound goes to infinity. Hence the limit as b goes to infinity of this proper integral with variable upper limit b of function g actually is infinite. So therefore this function cosine of x over x is not Lebesgue integrable over semi-infinite interval pi over 2 to infinity.